Hello, everybody. Welcome to our presentation for the Intro to Biomedical Technologies course here at USF. Today, we will be presenting about tremor relief devices for neurological movement disorders, specifically for people who suffer with Parkinson's. To start off this presentation, we will be starting with an introduction. Our team is consisted of Jacob, Baltazar, Andrew Padro, and Sebastian Palacio Mejia. We all got together because we had similar ideas and decided that a group to solve this problem would be better. Jacob is currently a junior chemical engineering student that worked on research and literature review for this project. Andrew Padro worked on designing and manufacturing the prototypes, and he is also a senior chemical engineering student here at USF. And I, Sebastian Palacio Mejia, I am a junior chemical engineering student that designed the first prototype and performed literature reviews on Parkinson's disease and neurological movement disorders.
The motivation for our project stemmed from personal experiences with tremors, as we know family members who struggle with tremors because of Parkinson's disease. A non-invasive treatment for these tremors can widely vary in cost and can also be an expense which is not covered by many medical insurances. Thus, we are motivated to create a device that is customizable, comfortable, and reduces tremors during daily activities. As mentioned, one disease which causes muscle tremors is Parkinson's disease. Parkinson's disease is a progressive neurodegenerative disorder that affects the central nervous system by causing a loss of dopamine-producing brain cells. Because of the loss of these cells, cognitive changes occur and motor control issues arise, such as tremors, stiffness, and slowed movements. While medication and therapy can help manage the symptoms of Parkinson's disease, there is ultimately no known cure for the disease. Since tremors are involuntary and can make simple daily tasks much harder, this led us to the problem to be solved. Due to tremors, individuals may struggle with writing, eating, holding objects, or keeping their hands steady during most tasks. Conditions like Parkinson's disease or other tremor-like symptoms can reduce comfort and independence, since certain tasks may require the help of another person. Many current support devices for tremors can also be bulky, uncomfortable, or simply too expensive for potential users. As such, our group wanted to focus on a solution to these problems that would be helpful, simple, and affordable. Our solution to the identified problem was to design an affordable arm brace to help stabilize the arm and provide relief from tremors. The tremor relief device supports the forearm and hand to reduce unwanted movement. In our first prototype, we created a hand brace which connects to a forearm brace via metal rods to allow for stability and control over tremors. These connected pieces would minimize any unwanted movements and provide support for the arm of the wearer. In our second prototype, we improved upon the design of the first by adding a gyroscope to the hand brace, which gave additional stability due to the added gyroscopic force. With these two prototypes, the goal was to create a device that could be practical, supportive, and accessible for regular use.
So now we will be getting into the prototypes. We have two prototypes to demonstrate and talk about today. The first one was our first idea. It does not work as well as our second idea, but it was a great start to understand how we could create this device that helps relieve stress for people who have Parkinson's disease or any tremor-related disorders. The first prototype, I went ahead and already put it on just because it takes some time to put on, but all you do is unstrap and strap it on for each part to have it attached to yourself. It has two main components, the hand part and the arm part, which are both 3D printed at the DFX lab on campus. And it's attached with two metal rods that are attached to one another, with of course the attachments here to make sure it doesn't go off. The idea behind the first prototype is that by creating stability in the arm, it supports the shakiness of the hand and restricts movements, as this part would hopefully restrict movements. And yeah, so looking forward to our second prototype, we thought that it would be better to have more stability on the hand itself, and essentially we still use the same attachments, but there's a lot of room for improvement. For our first prototype, it is not a bad idea, and it gave us a lot of motivation, and we learned from the first prototype to build the second one. Thank you. So there's several different advantages and disadvantages from our first prototype. Some of the advantages include that it's a simple low-cost device that's only about $18.50 USD. This is huge. A lot of these devices can come up from hundreds to thousands of dollars. So creating a more affordable option was one of our main goals, and it was achieved with this first prototype. It is also easily common to assemble with common materials. It's essentially just a forearm brace with metal rods that improve support. and it provided basic hand and wrist stabilization. Some of the disadvantages, though, include limited active tremor control, rigid structure that may reduce comfort over time, it relies only on a passive stabilization, and it has poor adaptability to different motion patterns. It is a very restricted device that does not have the best support, but for the price and for the assembly time, it is a great option for our first prototype, and we learned a lot on how we could improve this design to better support those types of individuals. So, what are the overall results from prototype 1? It demonstrated that a connected hand forearm brace improved stability compared to no brace. The metal rod frame provided a rigid base, however, noticeable hand tremors still persisted on individuals who suffer with this disorder. Further reduction in tremor amplitude required a more advanced stabilization approach. Essentially, this just means that we needed something to create more stability in the hand to reduce the amount of tremors or the amount of shakiness that a patient may have by creating more stability. These findings motivated the development of an upgraded system, which is incorporated in our second prototype that has a more complex stability system. So overall, it was a great first prototype, but there's still various different ways that we could have improved this product that we tried to improve on in the second type of prototype.
Prototype 2 was built directly on the first design but added a gyroscope to improve stability. The goal of this upgrade is to move beyond just passive support and create a design with better mechanical stability. The gyroscope in Prototype 2 was mounted to the brace as a spinning component to add mechanical stability. As it spins, it resists sudden changes in orientation because of the angular momentum. That resistance can help make the hand brace a little steadier and less affected by rapid shaking. We wanted to keep the wearable brace structure from the first prototype while making the design more effective. One advantage to this design is that it kept the strong brace structure from the first design while adding the gyroscope-based stabilization. This gave it better potential to reduce unwanted motion and make the hand feel steadier. It is also a more advanced approach while still staying within the idea of being a simple wearable assistance device. At the same time, it has also introduced some new challenges. Compared to Prototype 1, it is more complex and may require more setup and adjustments. The added components can also increase the total cost, and more testing is needed to evaluate the comfort and reliability. Prototype 2 improved on the original design by combining physical support with gyroscope-based stabilization. Because of that, it showed stronger potential for reducing unwanted hand movement and provided better tremor relief. It also gave us a clear direction for future improvements. Overall, this prototype shows that it is possible to create a smarter and more effective assistance device while still keeping the cost in mind.
After the design, construction, and testing of our prototype arm braces, these results led us to our final conclusions about the project and recommendations for future development of the arm braces. In conclusion, we successfully developed 2 tremor relief device prototypes aimed at improving stability and relief for people with neurological and voluntary movement disorders such as Parkinson's disease. Prototype 1 proved that a simple mechanical design can aid the hand by providing stability from the forearm to reduce tremors. Although Prototype 1 was successful in improving the feasibility and practicality of the arm brace, other improvements could be combined in the brace that could potentially reduce tremors even further. Prototype 2 showed enhancements to the first design by adding a gyroscope to generate increased stability of the brace and thus stabilize the hand even more. While this design was more complex than Prototype 1, the design represented another approach using the same arm brace that could result in greater minimization of hand tremors due to the combination of mechanical and gyroscopic stabilization. For our future recommendations to continue improving the existing devices, we should test the brace with more users and collect feedback on comfort and effectiveness to further reduce unwanted hand tremors. In both designs, we should improve the design to allow for less restriction of movement but equal stability. This could include reducing the sizes of the forearm and hand braces, or allowing the metal rods to move and follow the natural movement of the arm. For Prototype 2, we would refine the gyroscope system to improve contributions to overall stability. Refinements can be made to the gyroscope position as to allow for ideal tremor relief and stabilization. The weight of the designs can also be reduced by using better construction materials, and the fit can be improved with adjustable straps. For end-stage improvements to the design, we could also explore battery-powered or smart control features that are appealing to users while keeping the device affordable. One such feature could be to attach a motor to the gyroscope to allow for constant stability or initiation of the motor when tremors are sensed. With this, we can continuously improve upon our design and use our device to help those suffering from tremors.